Hello and welcome. In this lecture, we're going to discuss how to find percentiles in a normal distribution using z-scores, as well as a helpful rule called the 68, 95, 99.7 rule about percentiles and standard deviations in a normal distribution. So what is a percentile? If you recall, we talked about this a little bit in an earlier lecture, but to refresh your memory, a percentile is the percentage of observations falling below a given data point. So the median, for example, is the 50th percentile of a distribution by definition. So 50% of the observations are below the median. In graphical terms, the percentile is the area underneath the probability curve to the left of the point that we're looking at. So in the distribution that is on the slide right now, we are looking at the percentile at the observation 1800. So what percent of the observations are below that point? And in this case, that's about 84% of the observations fall below 1800, so 1800 is at the 84th percentile. So looking at a given distribution, how would we find the percentile of a particular observation in that distribution? We have a couple different ways of doing this. Let's start by talking about how we would calculate percentiles in R. I'm going to go over two different commands for doing this that give you slightly different output. The first is sort of the default bare bones command for finding percentiles in R. The command is called pnorm, and the command takes three arguments. The first is the value you want to evaluate. The second is the mean of the distribution, and the third is the standard deviation of the distribution. So in R, this defines what the normal distribution looks like. It has a mean of 1500 and a standard deviation of 300. So you specify those parameters, and then you also enter in the value that you want to evaluate. So the order of this is pnorm, the value you want to evaluate, the mean, and then the standard deviation. You can use that same syntax with a different command, the xpnorm command from the Mosaic library in R. And you say xpnorm, the value you want to evaluate, and then define the mean and the standard deviation. When you use the xpnorm command, this is going to give you some more output about your distribution. It's going to give you a graph and some more information about the percentiles of your distribution, whereas the pnorm command is just going to return the percentile you were looking for. So let's go through a quick demonstration of how I would actually do this in R, just to make sure that everything is clear. I'm going to open up an R script here that I can type into. I'm going to be using the Mosaic package, so I'm just going to go ahead and load that. So the first command that we talked about was the pnorm command. So we can say pnorm 1800. I can type this mean equals 1500, SD equals 300 if I want to. I can also, R will understand if I say just 1800, 1500, 300. That is, those are the arguments that R can take for this command. So if I run this, remember this is the example that we were looking at of SAT scores, where the mean of the SAT score distribution is 1500, the standard deviation is 300, and we considered a student who had a score of 1800 and wanted to know how well that student did. So let's run this command. So this is going to tell me that about 84% of the observations are below the 1800 mark. So, of course, about 16% of observations are going to be above that mark. I can also use, like I talked about, the xpnorm command from the Mosaic library. I'm going to type in, pass these same three arguments to the xpnorm command, the test value, the mean of the distribution, the standard deviation of the distribution. And the xpnorm command is going to give me some more information. So it's going to tell me if my variable is distributed normally with mean 1500 and standard deviation 300, then the probability of a value occurring below this point, to the left of that 1800 cutoff, is 0.8413, and the probability of a value occurring above that point is 15.87%. And again, it's going to give me this exact answer. This is the same as the answer the pnorm command gave me, but the xpnorm command gave me a little bit more output as well as this nifty graph over here. So if I wanted to say, okay, what's the percentile of a score of 2000 in the same distribution of SAT scores? I'm going to get a different graph. Okay, and we find that it is about the 95th percentile. So about 95% of observations fall below 2000, and only about 5% of observations are going to fall above 2000. And what if I wanted to find a lower score? Oops, let's run that. So if I have a score of 1,000 on the SAT, we find that that is only at about the 4.8th percentile. So only about 4.8% of people who took the SAT score lower than that in this distribution, and about 95% of people score higher than that. So I encourage you to play around with those functions in R. Try looking at normal distributions with different parameters, try trying out different test values, all that stuff, just to get a handle for how those commands work. The next way we're going to talk about of finding percentiles in normal distributions is using an applet. So I've given you a couple examples of normal distribution applets here. We're going to do a quick demo looking at the first of these, the one from the University of Iowa. This is that applet. And what we're going to do is we're going to enter in the same parameters that we were just talking about. So a distribution with a mean of 1500, a standard deviation of 300. You can see the shape of the distribution is going to change. It's going to become centered on 1500 down here, and its spread is going to indicate what the standard deviation is. If we change the standard deviation, if we made it smaller, the distribution is going to get taller and skinnier. If we made it larger, the distribution would get squatter. Okay, but let's stick with the example that we had. Then we're going to enter in a test value of 1500. And then this toggle here is going to give us an option to look at the percentile above that cutoff point, or the percentile below that cutoff point, which is what we've been talking about. Okay, so let's try the test value of 1800 that we were talking about. So this is the same answer that we got in R, that this is about the 84th percentile. And of course we can switch this and see that about 16% of observations fall above this point of 1800. And again, we could play around with different values here. We could see that if we got a score of 1600, that's about the 63rd percentile. And then that means that about 37% of observations fall above that point, and so on. So this is just going to give you the same answers as R will. I personally use R, so I don't have to go to a different website. I like R's output and stuff like that, but these are a fun way for you to play around, see different graphical representations of normal distributions. Okay. So the final way that we have of calculating a percentile is also the most analog way. And this is to use a table, a normal distribution table, also called a z-table, to find the percentile for an observation that we're looking for. So the first thing that we have to do to use this method is to calculate the z-score of the observation that we're looking at. So if you remember from a previous lecture, the formula for finding a z-score is the observation minus the mean of the distribution divided by the standard deviation of the distribution. So the standardized score tells us how many standard deviations above or below the mean our observation is. So in this case, we're looking at an observation with a z-score of 1.00. Right, our observation was 1800, the mean was 1500, so that gives us 300 divided by the standard deviation, which is also 300, gives us a z-score of 1, or 1.00. So the first thing that we're going to do is we're going to go over to this column here, underneath z, and we're going to find the first two numbers in our z-score, 1.0, and then we were going to follow out to find the second decimal place of the z-score that we're interested in. So in this case, we have 1.00, so we go out 1.0, and then this column here for the second decimal point of 0. And we head down here, and what we're going to find is that our z-score is 0.8413. So again, this is telling us the area underneath the distribution curve to the left of the point 1800. And we've standardized this using the z-score method so that we don't have to have a different z-table for every different possible normal distribution. We standardize so that we can just look in this one single standardized table. So if we had a z-score of 0.43 that we wanted to evaluate, we would head down this column to find 0.4, and then we would head out to find 0.43 in particular, and we would find in that case a z-score of 0.6664. So 66.64% of observations falling below to the left of whatever point that was that we were evaluating. So next, let's talk about an application of these principles, and we're going to consider a case study about quality control. So hypothetically, let's say that at a Heinz ketchup factory, bottles of ketchup are supposed to contain 36 ounces of ketchup. So that should be the mean of the distribution, and the standard deviation of the distribution is 0.11 ounces. And the quality control measure that the factory has in place is to take a bottle from the production line every 30 minutes and note its contents precisely. And if the amount of ketchup in the bottle is below 35.8 ounces or above 36.2 ounces, then the bottle is going to fail the inspection. It's not good enough to be sold. It fails quality control. So let's say that we want to find out, using these standards and this distribution of ketchup in ketchup bottles, what percentage of the bottles have less than 35.8 ounces of ketchup. The amount of ketchup in a bottle is distributed normally with mean 36 and standard deviation 0.11. So that's what we have in this equation in the middle of the slide here. Below that, we see a graphical representation of the area under the curve to the left of 35.8. So these are bottles that have less than 35.8 ounces of ketchup in this particular distribution. So let's calculate the z-score to find out what percent of bottles have less than 35.8 ounces of ketchup. So first we calculate the z-score by taking the observation that we're interested in, 35.8, minus the mean divided by the standard deviation, and we get a result of the z-score of negative 1.82. Once we've found that z-score, we can go to a z-table to find the exact probability to tell us what percent of observations are below that 35.8 threshold that we were looking at. So why don't you take a minute and pause this video and see if you can find out what that exact probability is using this z-table. So we're going to go down the column of z-scores till we get to negative 1.8, and then across to the 0.02 column to indicate the z-score of negative 1.82. At the intersection of that row and column, we see the probability of 0.0344. That tells us that 3.44% of the bottles of ketchup have less than 35.8 ounces of ketchup in them. So remember that bottles with 35.8 ounces or less of ketchup and bottles with 36.2 ounces or more of ketchup fail the quality control inspection. So what percentage of bottles pass the quality control inspection? Take a minute and use the information that we've talked about already in this problem and see if you can figure out the percentage of bottles that pass. To answer this question, we need to find two z-scores. The z-score for 35.8, which we already found, as well as the z-score for the upper cutoff of 36.2. And to answer this question of how many of the observations, the proportion of the observations that are in the middle of this distribution that pass the quality control test, what we can do is we can find the proportion of observations below the upper cutoff, so the proportion of observations that have 36.2 ounces in the bottle or less, and then subtract from that the proportion of observations that have 35.8 ounces of ketchup in the bottle or less. And that's going to leave us with this chunk in the middle that passes the quality control inspection. So we use the z-table to find the relevant proportions for these z-scores, negative 1.82 and positive 1.82. And then we're going to use this formula at the bottom of the screen to subtract away the top range of bottles with too much ketchup and the bottom range of bottles with too little ketchup. And what we're left with is the proportion 0.9312, or 93.12% of bottles that pass the quality control inspection. The last thing that we're going to talk about in this lecture is the 68, 95, 99.7 rule for normal distributions. So for normally distributed data and nearly normally distributed data, the following rule holds. About 68% of observations are going to fall within one standard deviation of the mean. So 68% of observations fall between one standard deviation below the mean and one standard deviation above the mean. About 95% of observations fall within two standard deviations of the mean, and about 99.7% of observations fall within three standard deviations of the mean. So while it's possible for there to be observations in normally distributed data that are farther away from the mean than that, they're very rare. And this tells us some interesting properties of normal distributions and where the bulk of observations are going to fall within that distribution. To make this concrete, let's look one more time at our example about SAT scores and the normal distribution of those scores. In the distribution of SAT scores with a mean of 1,500 and a standard deviation of 300, 68% of students score within one standard deviation of the mean, which means that they score between 1,200 and 1,800 on the SAT. 95% of students fall within two standard deviations of the mean, so that means that they score between 900 and 2,100 on the SAT, and 99.7% of students score between 600 and 2,400 on the SAT, where 600 is 3 standard deviations below the mean, and 2,400 is 3 standard deviations above the mean. That's been our lecture on percentiles in the normal distribution. Thank you for listening, and I will see you next time.